Hello, welcome to a presentation Going Under Down Under, Flank Margin Caves in Australia and New Zealand. Work done by myself and my wife Joan. The image pictured is from Rottnest Island in Australia, one of many small flank margin caves we were able to view during our fieldwork. If Australia and New Zealand are down under, does that mean we are up over? Just something to think about. Flank margin caves down under are not large, but they're extremely interesting scientifically, and the work that we are able to do in both Australia and New Zealand helped us figure out some scientific questions. We'll go to Australia first and look at 4 different areas, and then later on we'll go to New Zealand and look at 4 different areas there. First, we'll go to Bridgewater and Kangaroo Island in South Australia. Flank margin caves shown here are an eolinite ridge at Bridgewater. They are initially classified as fossil sea caves. Now, eolinites are just sand dunes made of calcium carbonate sediment, so they can make caves if they can be dissolved in a freshwater lens. The Southern Ocean is only a short distance away, and so here from inside one of the caves, looking down and out at the Southern Ocean, we're able to see why they thought they might be sea caves, since this part of Australia has been uplifting for the last few million years. But when you look at the caves, they have phreatic surfaces and massive speleothems and all sorts of features we associate with what we call flank margin cave development. As an aside, the individual pictured in this image is Ken Grimes, an Australian speleologist who passed away a few years ago, a very creative and imaginative scientist. Moving on to Kangaroo Island, which is off the coast of Australia. Because of its island position, Kangaroo Island is well known for its unique fauna and flora. The area we're interested in looking at is down here in the southern southwest corner of the island at Snake Lagoon, Admirals Arch, and Remarkable Rocks. At Snake Lagoon, we have once again eolinites, and they have flank margin caves in them at specific elevations that are tied to past glacial sea levels that have been overprinted by tectonic uplift. So in A, we see the north side cliffs, and if you cross over to the north side and look back the south side as in B, you see the similar caves at similar elevations mirrored in the cliffs that are there. The caves are small and partially destroyed by surface erosion, but they're interesting nonetheless, and they give us a measure of where the cave elevations were with respect to sea level, and help solve a controversy about whether or not there have been uplift on Kangaroo Island. Admirals Arch is a breached flank margin cave that wave action has opened up, and here looking at the extreme southwest corner of Kangaroo Island, we see the Kamintu Group basement rocks, and lying directly on them are the Bridgewater Formation eolinites, and this is one of the 2 entrances to Admirals Cave. Admirals Cave was originally described as a sea cave, but when you actually examine the cave, you can see that it started out as a flank margin cave and subsequently was breached or opened by wave action. In diagram C here, you can see the phreatic pocketing along the wall, and in D, you can see the original flat floor of the cave, which when sea level came up at the end of the last ice age, wave action breached open the cave and tore out the eolinites, exposing the Kamintu basement rocks, as we can see here. We can also see in B, we can see the gnarly stalactites that are forming today. The white arrows point to the same seal in all 3 images. It's about 1.5 meters long for scale. Nearby, only a few kilometers from Admirals Arch, are Remarkable Rocks, which is a granite outcrop, and the granites there have undergone pseudokarst modification to produce what are called tafoni, which are a superficial weathering product, not the same as normal dissolution. In B, you can see how bizarre these tafoni can become, and in C, you can actually go inside one. It's an actual true cave, and it has a ceiling pocketing to it that is very similar in its shape and morphology to the ceiling pocketing we see in flank margin caves in the Eolanites in the Bahamas, in this case Long Island, Bahamas with Salt Pond Cave. So you have to be careful. You can get the same morphology from different initial processes. Moving out of South Australia and going to Western Australia, we're going to take a look at Rottnest Island and at Cape Range. Rottnest Island is as close to a Bahamian-style island as any island we saw in our work in Australia and New Zealand. It's made up of Eolanites with interior water bodies. We'll look at an area between Green Island and Fairbridge Bluff, and we'll look at Herschel Lake area. This is what Herschel Lake looks like, looking down onto the island from a high proximity. Joan in the foreground for scale, and the hummocky dune ridges separating the internal water body from the Indian Ocean to the west. We found numerous flank margin caves between Green Island and Fairbridge Bluff. The sign here warns everybody to be careful and have proper equipment, but these are small flank margin caves, but they are in the right position to have formed during the last interglacial sea level high stand, when sea level was about 6 meters or 20 feet higher than present. We also found in the Herschel Lake area outcrops that have been tafoni formed into them by wind and other superficial erosion activities, not true cave development phenomena. Moving north to Cape Range, we're looking at the Cape Range Peninsula, which is an anticlinal ridge that sticks out into the Indian Ocean to the north. It has been uplifted since the Miocene, and it continues to uplift a little bit even today. It is mostly limestones with some other rocks involved that range in age from the Miocene up to the Pleistocene. In pictures A and B, we are looking at the east side and the west side of the peninsula, where the anticline has lifted the limestones out of the sea. And in B and in D, we can see the long linear ridges, which are coastal terraces from different sea level positions. In C, we can see how the crest of the anticline has been incised by fluvial erosion to create interior cliffs. Both these interior cliffs and the coastal terraces have numerous flank margin caves in them. Because this is an entirely limestone area almost, that when we have this fluvial erosion and we collect all sorts of talus, we end up with what's called a fanglomerate, which is a type of conglomerate produced by an alluvial fan. And in A, you can see how this rock, even though it's made up of all these different size clasts, produces dissolutional karst features as a regular limestone would. In B and C, we can get a close-up look at these clasts, and especially in C, you can determine that they are different colors and that they're all individually being dissolved, so they end up looking somewhat like melted ice cream, as we can see right in here, especially these two. We also have tafoni in the Cape Range area. The lowermost carbonate unit, the Mandu Formation, is chalky and somewhat silicious, impure, and it doesn't make very good flank margin caves, but it makes these features called tafoni, which are once again in these limestones wind erosion artifacts. But we have true flank margin caves, and while they're not long in linear extent, they can be quite large chambers. This is along one of the many watercourses up near the crest of the anticline. And these chambers, as I said before, can be quite large. The limestone has a fair amount of iron in it, so we get these beautiful red, orange, and yellowish colors, and a lot of interesting phreatic morphology associated with the flank margin process of cave development. Many of the caves can be found in all elevations, from down in sea level in the Pleistocene rocks up to the younger portions of the Miocene rocks high up on the ridge crest. The caves are short and simple, which is a measure of the fact that the freshwater lens and the sea level was held at specific elevations for short periods of time, so cave development was terminated when sea level fell. We found some interesting things that we've not seen before in caves, such as this pissing stalagmite, unusual given the arid climate. They had a tropical depression come by, release a whole bunch of rain, they had flooding, and then the water percolated through the rocks and ended up pinned under this crystalline stalagmite coating, and under pressure the water found an opening out and is squirting out into the air. So that's where the name comes from. In addition, when these limestones were being laid down in a lagoon, they were burrowed by invertebrates, and those burrows became infilled with sediment. That sediment cemented more strongly than the surrounding rock, so later on, after uplift and invasion by the freshwater lens to dissolve the cave, we end up with these unusual, gnarly-looking features which are not stalactites. They are infill burrows, which means they are not speleothems, they are speleogens. They're part of the initial cave-forming process. So while we have a lot of large chambers, as I said before, not many of them go for any great distance, but they are spectacular and they exist in the thousands, and survey has just begun to document them properly. And of course, in Australia, you've had a human habitation there for more than 50,000 years, and this cave contains Aboriginal artifacts that have been dated over 40,000 years, with the Indian Ocean in the background. Well, let's move on to New Zealand, Australia's eastern neighbor, because we had able to do a fair amount of work there. We worked on both North Island and South Island. We're going to talk about the Raglan area and the Napier area on North Island. Then on South Island, Kaikoura and Punakaki, although as you can see from the other numbers, we looked at a variety of sites on both islands. Raglan Harbour in North Island is a very interesting place to do field work on the coast because the tidal range is around 3 meters, which means you have to time your timing well in order to get in there and do the work and get out before the tide rises. So these places where Joan is standing or peering in would all be flooded by water at high tide. Item D, panel D, is interesting because the white marks on the ceilings and walls are scars of where modern oysters were collected by the locals. But this is in a limestone which itself is a fossil oyster limestone. So you have modern oysters growing on fossil oysters, which is sort of interesting. Moving to the east coast at Hawke's Bay in the town of Napier, we have the Whirinaki Caves. Now these caves formed the last 3,000 years and they were uplifted 2.4 meters by the 1931 Napier earthquake and uncovered by modern wave erosion. So while the caves are not big, as you would expect, because they're only had 3,000 years in which to form, they contain all the phreatic signatures we associate with flank margin caves. They cannot be vado structures because the top of the ridge is an impermeable mudstone. So while they don't make really great maps because the caves are short, what's interesting is before the earthquake, these were down at sea level, and this area contained a freshwater lens that was dissolving the caves. After the earthquake pushed the land up, of course, the freshwater lens drained away the new lower sea level, and wave energy chopped into the newly exposed hillside and brought the caves out to where we could see them. Moving down to South Island to Kaikoura and Punakaki, at Kaikoura, the limestones are highly deformed, and this deformation has fractured them to a great deal, allowing groundwater to move through them pretty uniformly to make flank margin caves. Kaikoura Penguin Cave is an example of one of these caves, and what we see here is the wave-cut bench that has been formed the last 3,000 years when sea level came up to modern levels and carved back and breached the hill, exposing the cave entrances. I was able to capture a 1.5 meter penguin for scale in this image, something I've not seen in caves before. If you look at a map of the cave, you can see that it's more rectilinear than we normally see in flank margin caves because of this predominance of fracturing that's occurred in the rock. And the penguin was situated right here, and the photograph was taken from over here. Going to the west side of South Island, north of Punakaki, which is a major tourist spot for the pancake rocks display there, we found Tube City caves and a number of other cave sites along this coast at Limestone Creek that had not been previously documented. And what we see is the same situation we had on the east side of the island at Kaikoura. We have a broad wave-cut bench that has come in and cut in to this hillside, exposing the flank margin caves. And the flank margin caves are located on a constant horizon all the way through the outcrop. What's interesting is that these lines are fractures produced by the tectonics. The actual bedding is this line coming through here, and we get these beautiful phreatic structures inside the walls of this hill. And once again, not long caves, but interesting to see that they're there. So basically, the lesson here is that if you go where no one goes, you find stuff. This is that Punakaki rocks a little south of Limestone Creek, and the spot we were unable to get down and look at some of these caves, which are sitting here, which we assume are flank margin caves. Ran out of time. So if you have questions about what we have seen today, you can contact me at jem2@msstate.edu, and we have scientific publications of all the areas we visited today, and if you want to see some of those, just let us know. Thank you for joining me today.